Hello, everybody, and welcome to this stream by the one, the only, the epitome of scuffed streams. It's me, Darjan. So, quick note yesterday I streamed, and if you joined, I'm sorry for everything that happened. If you were not and you are not even able to watch the VOD on here in Twitch, and you figure out that you can't find that VOD in YouTube, the reason is that yesterday the stream was played, absolutely played by little mishaps. So soon after the stream started, for no reason, the mic audio disappeared for about 10 minutes. Then it went back. I don't know why. From my side, it still looked like I was speaking. So I don't have any clue whatsoever about what happened in that regard. Then, like 1 hour later, the video just froze up. For a few minutes, I wasn't paying attention, to be honest, to the monitor where I have OBS. So I didn't see that the video froze for a few minutes. And then, once again, for no particular reason, once everything was going fine, the stream just got disconnected. So I decided that it wasn't even worthwhile to work with the recording because it was missing audio in some places, video in some other places. So it was a kind of a mess. So today we're going to do something similar to yesterday. So the first thing is I'm going to introduce or reintroduce what we're going to do. You may have seen something in the title, the stream title, but let me show you. What is this about? So L systems are a way to basically have computer graphics. It's a mechanism for computer graphics that work by having a grammar and then running the grammar recursively a number of iterations. And when you print the result, you can get things like this. You can get things like classic fractals, fractal curves. If you are very good at it and you create more complex grammar system, you can even create something resembling plants, and not even in 2D, which is what we're going to do, but for very clever people, they can do it in 3D. We're not going to arrive to the 3D. We're going to keep it 2D. But I think it's a very interesting project because, first of all, it involves a very simple grammar, and we are not going into parsing a grammar. I will show you later. Then once we have the grammar, it's just a matter of iterating symbols. That's easy to do. Then we are going to map those symbols to turtle graphics. Turtle graphics is a way to describe a drawing by imagining that you have a turtle on a paper, on a piece of paper, and that turtle is moving around. That turtle is actually a cursor, but for some reason it is known Turtle Graphics. So shout out to Viral, Verad, or poor guy's name, and his twin AI daughters. So yes, turtle graphics. And with those turtle graphics, we are going to print it out. The last point is, where are we going to print it out? Well, at the beginning, thanks to Macro Quad, I'm going to print it out directly on the screen. But the advantage of Macro Quad and RAW is that you can actually that you can compile to WebAssembly. So the last goal of this project is to have a mini local website that basically is just an index.html plus some JSON that calls our application as it is compiled in WebAssembly. So we can actually print this in a browser, which I think is an awesome achievement for this project. All right, so that's our goal for the project, meaning for the next streams. What did we do yesterday? So yesterday we started with the L system, with the grammar, right? So we achieved the ability to create a rule set in which we add variables, constants, which for this example we don't need any constant, an axiom, and some rules. What are those? Let me go back. Those are basically the way you describe an L system grammar. Is you provide a list of variables. Variables are symbols that can go into the left side of a rule, meaning that when we iterate the rule set, we're going to see if there is a symbol that is the left side of a rule, and we're going to change that into the right side of said rule. So those are variables. We can also have constants. Constants are symbols that are also valid in the rules, but they are not expanded in other iterations. They're just there. The reason for using constants is in the context of using turtle graphics, because even though they are not going to expand to anything, they can be mapped to some actions in the turtle graphic system. Like here, for example, they were mapped to, I remember, to push and pop from the stack. Here it is. Push and turn left, pop and turn right. So those are constants. They can have turtle graphic actions like variables, but they cannot be expanded in rules as variables. Then we have an axiom. An axiom is the seed, the starting point. It doesn't need to be a single variable. Let me show you an example. Here we have an example in which the axiom contains 5 symbols in total, 3 variables, f, g, and g, plus 2 constants, 2 dashes. So as you can see, we're able to write a rule set with variables, axioms, rules. Yes, we can also do constants. Then we lock the rule set. This is basically where syntax checks are put in place. Like, for example, that for every variable we have defined a rule. including the axiom, of course, and things like that. And then we call iterate, that basically does some iterations at the moment only at the symbol level. So let me show you an example of that. So this is the rule set in symbolic format, right? The way we can see the basically using the debug function in Rust. And then this is the result of 3 iterations of this rule set. Why 3? Why not? This rule set is one that appears in the Wikipedia, and the 3rd iteration, so this result matches the one in Wikipedia. So we know that we're doing our system correctly. However, this is the implementation of the rule set as we did yesterday in the stream. But here's the thing, I don't like it. I liked it yesterday. I mean, it is functional. But I realized that there are 2 main problems. Let me show you. The first one is that the fact that in the rule set we have variables and rules. Now, for a grammar to be correctly written, a variable should appear as the left-hand side of a rule once and only once, meaning that the list of variables is no more, no less than the collection of the left-hand sides of these rules, meaning this is redundant for the most part. But it gets worse. When we are going to do the iterations, which is the heavy lifting, we need to get the rules for every symbol that we get, right? And then produce the right-hand side of that rule. But how do we get the rules from the list of rules? Well, by using a binary search. And you may say, hey, that's good. Yes, actually, yesterday we started with contains, which was just a linear search, to a binary search. And you say, well, that's a pretty good job. Well done. But here's the thing. I think that we can do much better. Remember that the difference is that in a linear search, the order notation, right, for a linear search, so how many operations, how many comparisons we need to do for a linear search is order n, while with a binary search is in the order of the logarithm of n. And given that typically we have 1, 2, 3 rules, these are good numbers, right? What if we could use a hash table? So it is order k. I have an issue with hash tables in this context, and the issue is the following. The key for the rules is, the key for a rule is the symbol that appears on the left-hand side is a single byte. So just the cost of hashing a byte, computationally speaking, can take more CPU than just using the key directly. So obviously, direct table, I think that could work much better. So what I want to start with today is by basically rewriting the implementation of the rule set using a direct table. And you're going to wonder maybe, okay, but how can we do that? So we're going to add some restrictions, but you will see that it's basically like a hash table of sorts. But I'm going to call it a direct table. That's why I have this question mark, because it's actually a hash table, but with the fastest hash ever. So, 1 second. I'm going to note. Here. All right. So let me add the music. And let's put ourselves to work. So we are not going to use the rule set. 1 second, I'm going to change something in the filters. Okay, I like the music. But I'm going to increase the release. So if I take a breath while I'm speaking, the music doesn't come back up immediately. I think that's going to work much better. All right, so let's start with a definition of the rule set. Okay, at the moment, our rule set is not going to have anything. We're just going to build the rule set. And now, as we are building the API, and we'll see what do we need for that. So we're going to implement the rule set. The first thing that we're going to do is implement the add variable. With the text, the symbol being a character. And now what we're going to do is when we're going to have a restriction in about which symbols can be used as variables. And basically we're going to have an index which is going to be taken from an internal private function. Okay, and this one obviously can fail, right? Because there will be characters that we're not going to map into index. So that means that this can result in an error. So once we have that. Sorry, that was one way I was going to do it. And then I thought that's not the best way to do it. Let me think again. Yeah, no, we're not going to do that. So what are we going to do? We're going to accept any characters to be symbols whatsoever. So what we're going to do is we're going to create what we're going to call a token. Okay, there is going to be a token that contains the symbol. A number. And the number is going to be we're going to have a collection of tokens and have that. Tokens is going to be a vector of tokens. All right, so basically each token is self-described with its position in the token when it's going to be added there. Because obviously when we do this and then we do self tokens push of the token, right, the token is going to land in this position. That's a good way to put it. Why are we doing that? Because now that means that tokens is going to map the symbols that are going to use in the axioms and the rules into numbers. So internally, the rules, so both the axioms and the rules are going to be written in terms of numbers directly. And that's why this table is basically doing a direct table translation instead of using binary search. We're just going to go in, we're just going to pinpoint the position in the index. Well, first of all, we need to do something. First thing that we're going to do is that if we have locked the rule set, then we cannot add any variables. It is effectively locked. So we need to return an error that is locked. That's the first thing. The second is that if the symbol has already been defined, we're going to return also an error, in this case, already declared of the symbol. Okay, so let's take these two things out of the way. Now, let's continue. And yeah, token hasn't been described yet. But we're going to also do another thing, is that we're going to in the rule set, we are going to already pre-allocate the rule for it. So how is our rule is going to be, how is the rule going to be described? So now, because the index in the rule vector is going to match the index of the in the tokens for the precursor, so from the left-hand side of the rule, we actually don't need to store in the rules the left-hand side of the rule, only the right side. So how do we describe the right-hand side? Once again, by using those numbers, meaning that the rules is a collection and each of the rules is a vector of numbers. How many numbers? I don't think we're going to have more than 256 or 255 rules, because we're not going to have those many symbols, to be honest. So this is going to suffice. And that means that we're going to push here an empty rule. Okay, so basically what we are saying is that when we're adding a variable, we're just going to add it as a symbol and have an empty rule. But here's the thing. What about a constant? So instead, what we're going to do is we're going to create an enumeration for the rule that is either going to be constant, meaning there is no rule because this is a constant, and if it's a variable, then inside is where we're going to have the vector that contains the right-hand side of the rule, meaning that this is a rule. Expect vector. Oh. Okay, and for the moment, we're going to define instruct token to have a symbol and we have an index, which is going to be a U8. So the last thing that we need is this function symbol exists. And the way that we did it yesterday was we define partial equality for the token based on the symbols being equal. So we could use the contains function. And I think we're going to do the same. We're going to implement partial equality token. No, we self model set symbol equals model symbol. So now we can implement how it is called symbol exist. And this is just simply self tokens contains symbol. Oh, token. And there we have it. So we have implemented how to add a variable. Let's do the same with add a constant, even if we don't have that in the rule set of the example. So once again, we check that the rule set is not locked. We create a token with the symbol and the index. If the symbol already exists, it has already been declared. And if not, we push the token, and now the rule is just constant. Very simple. Basically, this is the only different line, so we can actually create a private token. Is and output. Okay, so basically what we do is all of this. We create the token, check this, we push the token, and then we push the now this first because it's expecting that. So the reference, and it's a shared reference, makes sense. So Let's derive no. No, I'm just going to pass it by value. The reason is I think that the compiler is going to make a better job. If I do it like this, meaning that now add variable is actually self token of the symbol and the rule. Being this, and for the constant, there we have it. Much elegant. Sorry, more elegant. The next is set axiom. So to be honest, the axiom is actually like a rule in the sense that it is a right-hand side of a rule, being the starting rule. So the axiom is basically from empty, what is the first rule that is applied, the first production. So basically an axiom is just a vector of number. But it is described as a string. Okay, so what do we need to do? Well, first of all, we need to do exact same thing. We need to do two things. Firstly, of course, if the rule set is locked, we need to return an error. The second condition changes now, and this if the axiom has already been described. So if it is not empty, the axiom is already declared. Now, the problem is that we have defined the error already declared with a char. So we cannot use this error for the axiom. And we had one error specific for that axiom exists. So that is that. So then what we need to do, we're going to create our local axiom. And what we're going to do is we're going to create our axiom. And like we did here in the rule set, where we delegated the parsing of the right-hand side to a function, Axiom with a U is the ship from Wally, I think. So if we get the axiom, then we just simply, well, we need to find the left-hand side first. Yes, no, this is the axiom. We just need to set the axiom to be that, and that basically solve the problem. But of course, we need to implement this method. So how does it work? Well, first of all, we're going to create a right-hand side, a proper right-hand side, which is what we want to turn. And then what we do is we're going to iterate over the characters in that representation. So for each of them, in an axiom, we need to make sure that those symbols exist that have been declared either as constants or variables, but for a rule to be correct, so not for a rule, for an axiom rule to be correct, there has to be at least one variable in the right-hand side. However, because that is not true in the right-hand side of a more general rule, this means that we either have to that we need to keep track only for the cases in which we're looking for an axiom, or we do nothing of the sort, and then here we validate the axiom, meaning that we take a look at those things if that one of the symbols in the rule set is a variable and not a constant. All right, so for the parse, what we're going to do is we have a symbol. So now we need to find that symbol in the list of tokens. And because we're just pushing new symbols as they go, they are not sorted, we cannot do a binary search. This is the part of this implementation that is actually slower, but it is done only during the parsing. So basically the part is going to be slower, but then the iteration is going to be faster. That's my thinking. here. So we're going to match self tokens fine. I'm sure that we used this function yesterday. I don't know why it doesn't auto-complete it or show me the help, and I need the help, so just it's nice. Hmm. I was almost sure that the function was called fine. Fine key addition point. Oh, contains. This is a boolean. Oh, yes, we use this one. Any. No, no, that was the problem that we had yesterday. We use any. Any also returns just a true false. It didn't work, and I tried to do something, and then I found that it was fine. If it's not in slices, it's in vectors. No, we have it. We had a fine. I cannot believe it. Yesterday, we implemented it in a linear search, and then we changed the linear search to a binary search. That's why I know we had that. Because it's from an iterator. Iterator fine. So here. And fine returns yes. The option, yes. Okay. Here it is. So now for the iterator that we have is a function. that is going to receive the token because we are iterating over the list of tokens. And we're going to say yes if that token symbol is equal to our symbol. Okay, so if we don't find it, so actually we're going to make that into another function. Fn find token serve and symbol char, and it's going to return directly like the we're going to have an error. And that is going to be the position. So if find doesn't find the symbol, we return not declare. And if we have some returns the index, right? 0, 1, 2, 3, 4, 5. Yes, it's the index. But in a token, the index is its internal index, so both works. So now you may be thinking that this is badly written because there is a way to do this properly. An OKR transforms the option into a result mapping some V to OKV and none to an error, and we provide that error. The error being this. Okay, there is a mismatch of something. Yeah, here. I know it's a problem. Mismatch types, expected enumeration of U8, found enumeration result, and token. I mean, so find is not doing what I was looking for. So we actually need to do the match. You know what's the problem? Cannot move out of share mode because T has token. But I'm using a reference. Oh, yes, the problem is when the referencing. So we're going to put the graphic on. Come on. That's what I did. What's the problem? Oh shit, the problem wasn't there. The problem was here. The data is moved here. All right, so now we have this function called find token. So now what happens is that we're going to transform the representation of the rule. Let me show you. So axiom was an A, right? So because it was added first, the variable, so the token is A0, meaning that in the list of tokens, in token 0, we're going to have a token saying A0. So we're going to change the this representation of the axiom into just a vector saying 0, representing token 0, which is the A. And that's all. So now we have the parse, and the only thing that remains is to validate the axiom. So remember, the difference between a general rule and or a right-hand side RHS, the difference between the general rule and the axiom rule is that in an axiom rule, at least one of the members has to be a variable. So I think that can be implemented with a self axiom any, no, any, not directly as an iterator, any, and given an element, if self tokens of that number, sorry, not the tokens, the rule, the rule for that number has to be a variable. So that is something that I think can be done with the matches macro. Let's try that. Oh, yeah, this is a boolean. And in the previous implementation, I think I used empty production, meaning that this action, if it doesn't contain any variable, is not going to produce anything at all. Oops. So now we have defined an axiom as just the right hand side of a rule, but with an extra validation because it needs at least to have one variable so it can actually produce something. And that being said, the stream is 1 hour ish now. So as per usual, we're going to take the stretch and hydration break. Let me put that on the screen. There. And I will see you in a couple of minutes, but you yourself, be kind to yourself and also stretch or at least walk a little bit and drink water. Okay, so once again, I will see you in 2 minutes. multiple like within Axiom, so they call the production. So given a precursor, you get this production. Obviously, we start with the first condition. If it's locked, it doesn't work. Then we need to actually find the token for the left-hand side. Oops. That's what I meant. So we're going to try to find the token for the precursor. If it doesn't exist, obviously that's a failure, but this is also important. If the rule corresponding to rule index has already been defined, so it is not empty, we return an error. In this case, the already declared for the precursor. What's happening? Oh. I knew that there was something wrong. Oh, for a rule. Oh yes, that's actually a good catch. So the rule is not just directly the vector. So what we're going to do is to do a match of this. If it's a constant, then that's directly an error. We cannot use a constant for a rule, because that would provide an empty production. And for a rule that is a variable, then if the rule has already been defined as a variable, because remember when we add a variable, we create it with a variable of an empty vector. Obviously, when we are going to add the rule, we're going to override that rule with a rule variable with a proper vector. So if that is already happened, if the right-hand side is not empty, then the rule has already been declared. Mm-hmm. Match arms, having compatible, I don't care. I'm not returning. Oh. So now the error here is that consider borrowing. Hmm? Okay. That's the second time today I'm beginning to lose track of the borrows. That's not good. Anyways, so with that, we have the rule index, and now what we need to part is the production part. We know how to do that because that's the right-hand side parse. So the last thing actually that we need to do is self rules of rule index as each size is equal to rule variable of self HS parse the production with, of course, catching any errors in the way. Yeah. All right. So basically, defining a rule is changing the entry that we had for that rule that was previously a variable with an empty vector to now a variable with a non-empty vector that is defined here. That being said, is it actually true? Are we testing in any way, in any place, that the right-hand sides are not empty strings? We don't, and both are passed directly to RHS parse, so we can validate that here. If this is empty, return empty production. All right. So now I'm happy with that one. The next method is lock. That's very simple. In theory. However, I think that there was something that I did, and I think it's a good idea. Let me show you. In the other implementation, in log, we did tests. So we made sure, for example, that the axiom wasn't empty, and that for all variables, they had a rule attached to them. So let's do that, but in this implementation. So first thing first, for the axiom, right? And if the axiom is not empty, once again, we need to make sure that, well, for constants, they were defined, but for variables, that they are not empty. And I think we did something like that in validate axiom. It's something similar to this with any. It's basically self rules into an iterator. So, and you know, all which is something that it's an iterator that runs on all. No, we can do with an n and the negative. So if for any rule keep in mind that what I want to do is something kind of crazy, and in reality, this should be in function to make it more readable. So I'm going to make a in which we're going to have a function called isInvalid rule that receives that just receives a rule. It returns a boolean. So that boolean is actually going to match the rule. So in the case that the rule is a constant, return false, because remember the function is called invalid. It's the invalid, and for a rule that is a variable on the right hand side, it is invalid when it is empty. All right, so in case any rule is invalid, that is going to fail. So empty production. And if the axiom is correct and for every token, there is a rule, and that rule is either a constant or a non-empty variable, so they are all valid, then the only thing that we need to do is to lock it down, right? Is what we did here. This empty and check the rules, only that now instead of doing a for loop, we're using an iterator, and just self locked. True, and everything is correct. What's the problem here? Arguments are incorrect. Oh, I was already. Okay, it was the other way around. I'm losing track of the references today. I think that's because I'm trying to be too clever. All right, so now we have implemented lock. I think that there are only two methods that are missing: new and iterate. Let's implement new first. Now that we have the majority of the API is stabilized, so we know that the content of the object is not going to change. So this is a pub const function new and self, and we're implementing define or set. So this is a little trick that allows you to have two constructors when your constructor don't need a argument. The default one, which is nice to have, but another one called new. Only that new is constant, so you can actually could create a constant rule set even if that doesn't make any sense, right? Well, that's the idea. So for self, we need is lock to false. And the others are just empty vectors. Okay. We're not, okay, this is interesting because I missed that, and that is going to be a very clever thing that we need to do. But in order to understand how to implement debug, we're going to first implement iterate. How did I implement iterate? U8. You know, makes sense. So what happens is the following. There is an input. That input is a vector that is empty and it is a vector of the same type as the axiom. Sorry. In fact, it's going to be equal to the axiom, but not yet. Oh yes, it has to be. And the output is going to have the same type as the axiom or as the input, because the output is going to become the production of right hand sides, and in the next loop is going to actually be copied into the input. Let me show you. So first of all, we are going to clear the previous output. This is a mistake. That I did yesterday. So, okay, so why output is equal to axiom clone to wipe it out? Because in the case the user selects 0 iterations, then we output the axiom, which is what we should with regards to if you take a look at Wikipedia page and you take a look at iteration 0, and that is equal to that. So now that the output is clear, let's build that output from the input. All right. So remember, what do we have in all these rules that we have transformed? Numbers, right? Unsigned eights, which are basically the indexes to the rules. So now the only thing that we need to do is to match that index as a rule. And if it is a constant, we just need to push itself. Otherwise, what we need to do is to append A copy is important. A copy of the right-hand side. Perfect. And once we finish, so that we have our outputs complete and we don't need input anymore, we make input to be a copy of the output for the next round. Once we are finished, let me show you the function from yesterday was basically the same. We have the input to be equal to the output, and we have the for loop for the iterations. We clear the output, and then we were using the rules, but we use a function for that. I prefer it this way because, you know, it's not all the time that we need to append. And then we clone the output into the input, and then we will finish. And then when we finish, we have, oh yes, I forgot about this. So this function actually made it have a return value of bool. So if it wasn't locked yet, we would return false. No, we cannot iterate unless it is locked. So printing. Now the issue with printing is that because inside the rules we have transformed all the so in all the right-hand sides, right, all the axiom and the variable rules, we have transformed the letters, the symbol, into numbers. Printing out any rule or even the production is not going to look pretty. So we're going to make an internal method that is called right-hand side as string. And basically what it does is we're going to start with an empty string. And then for each index in right hand side, we're going to push into the string the token. We have not used the tokens list a lot, but we're going to use it now. We're going to use the token symbol, the character. So we are building the this as we go. Now that I'm thinking about it, because this is going to be a one for one. Let me try. We're going to have the right hand side. We're going to make an iterator, and then we're going to map for each index into sub tokens index plus size symbol, and then we're going to collect. Yay! Looks like I'm better at functional programming in Rust than in actually using references. So edges as a string. So now here, when we have finished doing the iteration, we can try to print it out, right? Like we did here. And not the output, sorry. Sub here, H is a string. Um, oh, sorry. And was a reference to a vector, perfect. Okay, so let's try. Okay, 144. We create a reference that is immediately dereferenced. Okay. And replace the closure. Oh, that's absolutely right. This if has identical. Okay. Oh. That's correct. RHS as a string. It doesn't need a vector. It's need this. And then 142, this is his words. It says if this oh, that's absolutely correct. This is what it means. Cool, cool. So cargo big, cargo creepy. And finally, let's try. And as you can see, now the output is A, B, A, A, B. For the third iteration of this rule set, so let me show you. It is this one. And third iteration is A, B, A, A, B, B, A, A, B. So we did it. So now the only thing that we're missing is implementing the debug rule set. Let's copy an implementation of debug that I had. Oh, not of debug, of display. Use the right macro. Am I right? Yes. So we have a rule set. In this rule set, you have first is locked. Yeah. So we have is locked. Then we have the tokens. Now for the tokens, what we need to print is self Self tokens, which is a vector, we iterate, then we map every token, which is his symbol. Which is basically something that we did in the printing function. Yeah, this is small enough. Collect. All right, what's the issue? Oh. There. All right, so what's the product? Type annotations needed multiple implementations and this from iterator chart found in data, from box, data, for a string, consider specify the generic argument. All right, so with that, we have printed out the tokens. The next thing that we need to print out are the rules. And for the rules, what we're going to do is again, we're going to iterate, and then we're going to collect into a new vector. And we're going to map the rule into a string. That string is going to be is going to be no, that's self and the index of the rule. So what I'm going to do is we're going to start with self tokens. Its index is size symbol to a string. And then we're going to append that. And then we're going to append the edges as a stream of self. So no, that's not how it works. So what we need to do is need to match. So the problem with rule as a string is that not all the rules become, no, sorry. Yes, not all the internal rules become string, but we're using the back. So it just actually doesn't matter. So a filter. Okay. So what we're going to do is for a single rule, we're going to have an option string. So if the rule is constant, we return null. And if the rule is a variable that has a right hand side, then we return self tokens of index as size dot symbol dot to string dot append images. And that is the sum. We. Oh, yes. Index is on the right. So now what's the problem? Push str. Okay. And that means we don't need to Chrome. And let's look at this. Oh, so the thing is that this doesn't allow us to do composition. So we need to do this and then return some separately. The rule as a string. So we're going to use the filter map in which the return iterator yields only the values for which the supplied closure returns some value. And that iterator is self rule as string. Okay. So oh yes. This is not the correct iterator. This is from 0 to self rules length. That's the iterator map, filter map. So for each index, we do a self rule as string on that index and collect. And the break here is the argument is incorrect. Oh, interesting. as a vector of space. Hey, what's the problem? Oh, it needs okay. It is tokens, rules, and the axiom. Now the axiom is easy because it's self enriches as a string self axiom what's the problem? It's less. Okay. So I think we can print the rule set. So rule set is locked false because we printed out before the locking. Two tokens, A and B, rules A, B to A, B to A, and the axiom A. Yeah, so you see the only thing that cannot be undone is, or at least not simply, is fishing out which tokens are symbols, which are constants. But other than that, the basic idea, or the reason why we have spent the day redoing what we did yesterday, is basically that this implementation of the iterator, in which the input is just a collection of the indexes that link directly to the rule, is much faster than what we did yesterday, in which iterate had to call for each of the input elements a get rule for, and get rule for had to do a binary search. Okay, so once again, this is what I was saying at the beginning of the stream. This implementation that we have done today is way faster because iterate, which is what is going to happen more often than, because declaring an item happens only once. So we are paying there the price of a linear search. But then iterate is much faster because we have now a direct table to the iterations. So this is going to be way faster. Let me show you with 7 iterations. Right, so with 7 iterations, we should get this. And we get it. And once again, we make this very fast. So with that, we have implemented an else system what are the next steps? The next steps are, well, the obvious one that I yesterday said that we're going to do on Tuesday, which is to map or create a mapping between the tokens and Turtle Graphics. So first of all, on Tuesday, we're going to move a little bit out of the L systems, and we're going to just implement a very simple Turtle Graphics system with MicroQuad. And then the next, when we finish that implementation of the, when we finish with that implementation of the Turtle Graphics system, we will need to improve the implementation of the rule set by adding not only the variables and the constants, but for each implementation of a variable and constant, having the option to also add how does that map to Turtle Graphics primitives. So instead of having this as an output, when we're doing the here in iterate and we're doing an RHS as a string, the output actually becomes a quote-unquote a string, but not of symbols like here, but of the actual Turtle Graphics primitives that can be fed into the Turtle Graphics system and print things out like this, which is our code. All right, so yes, today it was a little bit of a bummer in the sense that what we have done is basically repeating what we did yesterday. Hopefully, fingers crossed, the mic has been working today, the video hasn't stopped today, and that means that I will have we will have the VOD in Twitch. We will also have the VOD in YouTube. As a reference, I explained today also this. That's a nice thing to have. So once again, what are the next steps? Next week, starting on Tuesday, and by the way, I'm going to change the schedule, and we're going to start the streams next week 1 hour before today. So we're going, not before, we're going to start 1 hour earlier than today for next week. And on Tuesday's stream, we're going to basically start from zero. We're going to forget about the L system, and we're just going to play around a little bit and make a small Turtle Graphics system that just can advance with or without drawing, but here in this article called Draw and Move, push and pop positions and angles from the stack, and turn left and turn right. Basically, that is the idea. That being said, when we reach that that point, you will see that there is an issue. The issue being that when we use MacroQuad, or you use in general any printing system, you are providing pixel positions, right? And the issue with pixel positions is something that happens. Let me show you here. Here in reality, this is this block. So if we print this at this scale, this doesn't fit on the screen. So one thing that I want to add to our quote-unquote simple Turtle Graphics system is an auto-scaling system. So this is just an advanced quote-unquote one, but depending on the scale, this will be printed longer or shorter depending on the size of the canvas and the bounding box. So one of the things that we need to figure it out when we do the graphics is to find out the bounding box so we can do the auto scaling. Okay, so that's the problem that we're going to start doing on Tuesday. Once again, 1 hour earlier than today. When we finish that tartographic system, then we're going to incorporate that tartographic system into the output of our production. And once we have that, the next step is to add another functionality for the rule set, which is to be able to be deserialized from JSON, meaning that giving a JSON description of the rule set, because as you can see now, we are setting up the rule set as code. The idea is to have a JSON representation of the rule set. So lastly, we can create a WebAssembly function in Rust that when called from a web page through JavaScript, and that JavaScript function passes as an argument the JSON representation of a rule set, as well as a number of iterations, the output on the web browser is going to be this. Okay, that is the end goal, in my opinion, for this project. I'm not going to add, colors, 3Ds, etc. At least not for this phase of this project. But I think that we are going to learn quite a number of things in terms of what here it was kind of easy. It was mostly the fact of moving from this implementation that needed binary search to one that is in which the symbols are auto-indexed, are self-indexed. So we can use tables to quickly find out the symbols, the rules, etc. That's basically the main feature that we did today. But once again, next week, we're starting with graphics with a library that firstly we're going to use it with native graphics in Linux, but that can also compile to WebAssembly. And then, yeah, so graphics, then JSON, then WebAssembly. All right, so I think that on my end, that was all that I wanted to do. Something that I mentioned yesterday that is still going to be true. I'm going to keep this repository as local. You know that for the previous project, I was uploading, or I was using a remote origin for the repository in Codebrew, but because I still don't know if the end result is going to be a binary crate, which is what we're doing now, or a library crate when we move to WebAssembly, because I have examples of using WebAssembly graphics both as libraries and as binary, so I still don't know. Depending at the end on whether or not we keep the binary crate or we create a new crate as a library crate, then that new crate I will put it also on Codebear for all of you to also have the source code. That's why for the moment I am not bothering adding tests or adding comments, nothing of the sort, because this is going to be basically fire and forget code. This is your typical code that probably it could have been created by an AI, but most likely they're not the AI unless you are very specific. And it would have kept the rules with linear searches, not even binary searches, and not even a table unless you add those details in the prompt. So I'm very happy to have written this code by hand. And yes, that's all for me today. I hope it has been helpful. I hope that we have praised enough to the Omnisaya and we are free of um, silenced mics and frozen videos. And if so, thank you very much for watching this stream with me. If you were not here in the stream, thank you for watching the VOD either in Twitch or in YouTube. And well, I hope to see you on Tuesday for the Fractal Graphics things. And but that's all from my side. So this has been the Prefect Dargen signing off.